This project will investigate the relationship between biology and computational design thinking as a tool to drive the design of a regenerative architectural solution, focusing on coding and scripting, 3D printing, and material innovation. I'll start by introducing the site, Sydney Olympic Park, located along the Parramatta River catchment with a strong relationship with its surrounding estuary. Estuary ecosystems have provided the Wangal people with resources for 28,000 years. During European settlement, the site underwent dramatic change and degradations in land and water quality. However, the 80s saw great remediation and renewal, preparing itself for hosting the 2000 Sydney Olympics. Today, it's a premier destination for sports, leisure, recreation, living, and nature conservation. A 2030 master plan will ensure Sydney Olympic Park becomes an active and vibrant town centre, whilst protecting and enhancing its public domain and parklands. It's a node between Sydney's two ever-growing CBDs, whose urban fabrics are quite dense. With a large percentage of conserved and protected land, Sydney Olympic Park is less dense, but faces pressures of mitigating urbanisation whilst maintaining ecological conservation and biodiversity values. There are four main wicked problems that the site is currently facing: more water, more salt, more people, and more heat. All have profound impacts on our health, livelihoods, and our supporting ecosystems. These four problems provide unique opportunities to design resilient and regenerative architectures that grow with the site, just as nature has for billions of years. The site is susceptible to dramatic changes in coastline over the next century. Altered rain patterns, sea level rise, lack of tidal exchange, and ocean acidification cause many issues, including algal blooms that suffocate estuaries, native fish, birds, and mangroves. While these wicked problems seem out of our control, there's a unique opportunity to problem solve here. Protecting these ecosystems will help protect us. The site has three main sectors: Armoury Park, Haslam's Park, and Bicentennial Park. The proposed Discovery Centre will be located within Bicentennial Park, as it has a strong connection to these vital ecosystems. Here are some photos from Bicentennial Park, different forms of inspiration from nature, and some photos of the existing Discovery Centre, which includes a small-scale building, elevated function hall, and two pavilion areas, with nearby bridges and walkways. The project will address three chosen UN sustainability goals that work together to design a regenerative concept: responsible consumption and production, life below water, and life on land. There's a unique opportunity to build with local and innovative materials, using water ecosystems to drive design and to further enhance Sydney Olympic Park's great initiative to protect local biodiversity in future development. Research and development undergoes two phases: studying natural growth patterns as a structural language and studying biocomposite materials such as biopolymer and mycelium that could work with the language. The chosen structural material language will drive the design of a Discovery Centre in Bicentennial Park. Biological growth is not uniform. It's differential, meaning it responds to differential stimuli and thus produces the formation of individual macroscopic shapes. You can simulate this pattern in Grasshopper by segmenting a curve and letting it expand without any of the segments touching or overlapping, by adjusting the parameters, number of segments, radius, and strength. I tested the differential expansion of a curve within a boundary, producing 10 iterations of 10 stages of growth. I stacked and lofted these, and then 3D printed the result in PLA. For prototype 2, I tested the growth pattern on a surface with different densities of growth. I simulated it on a range of surfaces, studying which surfaces could be ideal for this pattern, pinching and pulling shapes, convex bending. I did some 3D test prints to see how the prints behave with this pattern, testing flexibility as well as the limitations of this method. Moving on to materials, I looked into biocomposites as standard building materials have a significant impact on our environment and resources. First, I studied mycelium as a building composite, the root system of mushrooms that can be combined with agricultural waste to produce strong and versatile composites using a template. I tested the material by growing it myself to see how it behaved, but it was audited as biopolymers ticked more boxes for the final design. Cellulose-based biopolymers made from materials such as algae can be easily harvested on the site. These have been refined and 3D printed into modules that could form larger structures. From its state as a raw material through extraction and manufacturing to eventual decomposition, the material is grown from its environment, and if 3D printed on site, the architecture can also be grown from its environment. Some early concept sketches. The research led to an intention to design with multiple iterations of differential growth, including on a surface and as a solid using algae biopolymer. To support local production of the structures, I'll design a small yet expandable factory that will output biopolymer pavilions across the site. The public will be able to view the process and there will be less harmful algal blooms across the site. I decided to reuse the existing Discovery Centre, enhancing the main building and connecting it to the pavilion areas and function hall. The project will test the use of differential growth as a stack and lofted sculptural wall system and the pattern simulated on a surface, becoming rib-like pavilions over a block of program. The form comes from taking simple geometries, pulling and bending them to form arched pavilion shapes. Other pavilion structures can be scattered near and far that have similar formal quality to the ones over the building. The main building will house manufacturing, production, research, and education areas. The circulation corridor will include a public walkway within the columns and visual access inside, as well as linking to previous and function hall that will now be a cafe and education theatre above. This is a site located at a node, intersection of multiple paths, and a good spot to draw people in. A small road will be made to connect to the existing car park to help with vehicular and pedestrian circulation. This is the ground floor plan with the public walkthrough and seating area. Landscaping takes inspiration from the differential growth plan, another experience of this pattern. First floor with a viewing gallery of the sculpture walls and the green roof space. The southern elevation gives an idea of the scale of the sculpture walls, aimed to be a monumental spine to the new Discovery Centre. This section shows the internal space in that corridor as well as the pavilion structures on the other side. A concept model of the sculptural walls at 1:50 scale, testing them in clear PLA. This render of the southern facade with seating and bike parking. A render of the walkway connecting the classroom and lecture theatre. This render shows the seating on the northern facade. And some more renderings of the internal spaces and a close-up of the algae pavilions. Over the next century, the Discovery Centre building will expand and continue outputting pavilion structures across the site. As it expands, so will the education, classroom, and cafe areas too. Further, the pattern can be applied to existing bridges or structures on site as a parasitic structure to revamp existing, perhaps deteriorating infrastructure across the site to continue keeping the site healthy and functional. This drawing tells the story of how the growth pattern has been translated into an architectural language, using valuable resources on site to develop an enlivened Discovery Centre and localised fabrication lab to enhance education and infrastructure for studying this convergence between architecture and biology.